There's one thing about our source code, because all the stuff is already implemented. You don't have to re-implement it yourself. And those guys have used the cat-c library. Anybody here a developer of the cat-c library? Lucky you. Because I've reversed the library and found out that it is cat-c they are using. And then I said, wow, this is cool, so I can have a look at the source code. But actually, it was easier to look at the binary than the source code. And I'm not the only one thinking that, because the developers of Storm, you know, they include this encryption, as Mark mentioned. And what they did is, they added this encryption just before the send, and removed it afterwards because they couldn't understand what's happening somewhere else in this library, right? So nobody understands that except probably the developers, I hope at least. Okay, I'd like to show you some details about the reverse engineering. If there are people here that are into reverse engineering, some of the stuff is not so new, it's just standard, but my motivation is to get people into reverse engineering that are not already. All right? So if you find all the stuff interesting I'm telling now, come to our workshop tonight and we can show you a little more tricks, all right? Oh, which room is it? It's starting at 8 o'clock? A3. Well, we are there for questions, but we only have 10 seats, all right? Okay, the first thing you need for reverse engineering is best to have something that you can run in a debugger or disassembling program. My favorite is IDA Pro, as is the favorite of many other people. You should definitely get a copy of the free version if you want to start analyzing executables. And the debugger is crap, but what's cool is browsing the executables. And we used it to do the static analysis of Storm, which means that we looked at the binary and what's happening there, control flow and stuff, without executing it in IDA. And then you can rename variables and functions and whatever. And it's pretty cool to browse through the source code. But in, well, not source code, when I mean source code is assembly. Okay, so what we tried first is we built a decryptor for Storm in order to, when a new version is coming out, so that we can get a fresh copy of the code and have a look at it. Then we came across we got some hints from others, that we can just do a memory dump and reconstruct the import table, and it worked well. Because Storm is loading the whole executable in memory after unpacking, even with their headers. Okay, there's a second tool you need, which is a debugger. Because you may discover the logic using a disassembler, but you cannot really have a look at what values are inside the variables and stuff. This is pretty hard and takes a lot of time if you want to do it with just a static analysis tool. So what we did is we linked all the information we got from IDA, from our manual analysis, static analysis, and used them in the Immunity debugger. So that we got all the information from our static analysis tools in the Immunity debugger, which is a lot helpful if you can use names there and stuff. And here comes the cool stuff. Because all the Storm code is extracted into heap memory and run in heap memory. All right? And there's only one point where you can be sure that breakpoints stay where they are. And this is right after the start, right after unpacking. So we have built a small decryptor stub and a script that's watching Storm as it's getting unpacked. And once it's unpacked, we can install everything we want. And we used it for breakpoints, patches, and all other stuff like VM detection, patching out, and stuff. All right, those are two screenshots of Lord P, which we use for dumping. And the only thing you have to do is find the right memory region, the heap memory region, and reconstruct the import table. And then for Storm, this is only for Storm, not if you want to do general reverse engineering. But for Storm, it works very well. You get the whole executable. And even with some import or function or external references. Okay, but back to the main topic, as Mark has mentioned, we need some search hash to find the control server. And this is what Storm does. It looks for a specific hash, like any file, and the response or the answer to the search, search result, is telling you where the command server is located. And we need that in order to inject our own command server. For the older versions of Storm, with which we started, this was pretty hard because somebody had used a POSIX library that was linked, which was a Windows port, and they did some very fucked up operations. Newer versions, they are using the MSV CRT library, and it's straightforward. You can read everything out of there. And I suspect that Joe Stewart had to wait for publishing his details for so long because he could just read out the simple stuff, but I'd like to talk to him personally on that. Okay, what we did differently than others, we re-implemented all this in C because we wanted to take over Storm. So in order to be efficient, we had to do some debugging. We patched out all the timeouts, even some control sequences, so that we can come to the interesting parts more quickly. And we monitored the relevant functions. For example, send, when things are sent out to the network, so that we can intercept, check, is this the stuff we want to monitor? And if so, we looked at where are the buffers, like for example on the stack, and could crawl through the binary. Okay, as I said, the old stuff is pretty complicated. I wanted to show it to you, like this is our disassembly. There was some strange function, mix time, and what we could identify very easily was that the whole buffer that is used after this mix time is XORed. All elements are XORed together and all elements are added together. And this is how some excerpt from mix time. And there are strange numbers. At first we thought, okay, this is some kind of encryption. But if you have a closer look, you see that get system time is giving you the nanoseconds since 1601, the year 1601. And Storm wants to use Unix time. All right? So this is just some simple conversion, but it was easy to find a candidate. But all the stuff and seeing the logic behind it was pretty hard at first. It's a lot easier if you have a look at the newer versions. Right? There's just a call to time, and then you can see the days, years, months, day of week, and so are put into a buffer and XORed and added together. Okay, this is illustrated here. So what we need is we need the day, the weekday, month, year, low and high byte, and there's 2 checksums done on that. Furthermore, there are some pretty strange operations, like 2 of those date informations are divided, they are multiplied, modded, and so on. And this doesn't really make any sense. So it's just for obfuscation. And what was that question? Seems not. And the point is why this is working is because, this is actually the good point about Storm. Let's start differently. You know, the guys that are normally affected by Storm are not the elite computer users. And you know what's the biggest problem for those guys? Keeping their time in sync, right? And actually Storm does that for them, right? So, isn't that a great feature? Come on! All right, and Storm has to do this because the hashes have to be the same for all hosts across the world, right? And they are all getting the GM time, which is the same for all hosts in the world. And so all hosts for a specific day have the same hashes. Then you take specific information, do some stupid integrity checks like XOR all the elements, add all the elements, which is just some obfuscation, and some other strange stuff. And at the end, you use a static XOR key to encrypt the stuff, all right? If this is really encryption or not, I'm leaving this to you. Actually, it's a symmetric key encryption, but it's not very valuable. All right. As mentioned before, there are 32 different, and this is because of a random value that's at the end added to all those elements. And that's the whole magic. Here's the C code. As mentioned before, no need to take out your notepads and write it down now, because we are publishing that, okay? So we implemented that and looked at where do the hashes lead. Can we have other peers connect to us because we are very close to the hash? And what about the hash results? But the problem was at that point, the hashes didn't lead to any hosts we knew, right? So there were the search hashes which we could answer. We could be the closest, the best ones close to that hash. So we could practically say, we know where the file is that you need, all right? If the file is similar as the command control server. Okay, so what we found out is that there is no correlation between the result that gets returned after the search and the actual command and control server that is used. So there must be some information in the result that redirects all the bots to some other server. Okay, this gets us to the second hash we are going to look at, result hashes, because you're not getting an IP address in Overnet or a port or whatever, you're getting a hash as a result. And so we had a closer look at those hashes. And in order to get some useful information about those hashes, we used a debugger and did some data flow tracking on the static part to find the position, to find the function inside the original Storm where this stuff is parsed and what happens there. Once we found this function, it was maybe half an hour work or maybe an hour to get C code out of that. We had to redo it a few times because of the Kademlia library, cat-c, because it's using so many threads that you get totally confused by looking at it, right? So we had to do this again and again and restart the debugger, and to be a bit faster, we patched out some timeouts that Storm is using and the control flow, which we knew could be stepped over. And what we got as a result is that of the hashes, the result hashes, okay, that's now not the search hashes, that's the result hash we are getting back. The upper 4 bits are always random. They're just crap. They are not used at all. In the 0 bits of each byte in the hash, there's a checksum. The lower 8 bits are a sum checksum, all elements added together. The upper 8 bits are an XOR checksum. In the 1 bits, we got the port the client is connected to. So this is the actual port of the command and control server. And bits 2 and 3 is the IP address of the command and control server. And the whole thing is encoded using the same static XOR key as the search queries. So the good Storm guys implemented one static XOR key encryption and used it everywhere, right? Easy for us. Okay, here is the whole thing a little illustrated. I'm sorry for the colors. I lost some slides and had to redo them very quickly. I hope you're not getting blind now. Okay, so the bit number 4 is having the IP low bit. Then the next bit 3 has IP high bit. Here's the port and here's the checksum. So this is how it works. And knowing all this, right, this is the C code. Knowing all this, we were able to tell the bots where to connect to get commands. All right? First, we injected the search hashes, saying, we know the results, we know where your command and control server is located, and then we said, okay, the command and control server is our machine. And this is the actual code, which you don't have to write down, you know. Okay, and what happens then is the bot connects to the server we announced using TCP. There's a challenge response, another XOR key. This one is different now. And if this response is correct, the server is answering our requests. Okay, the whole thing is really highly encrypted. I don't know if you know the zlib encryption, right? Who of you does not know zlib in